In this short video we'll cover just a single topic of ultrafiltration. Remember, the kidney has two main functions: excretion, which means getting rid of nitrogenous waste, and that's getting rid of the urea, so this is all to do with urine formation. And then this osmo, referred to osmosis, water, regulating the water potential of our blood and body fluids. The excretion bit has two components, and they are ultrafiltration and this selective reabsorption. So this video is just going to cover the first of these, the ultrafiltration. So let's recap the structure. Here we have the Bowman's capsule, the first part of the nephron. Here we have the glomerulus, and again, be careful, this is the afferent, so blood is coming in here and leaving here. A for arrive, E for exit. Also again, as I said in previous videos, greater diameter of the afferent compared to the efferent. Blood that enters the glomerulus is under high pressure, or the better way and the exam way to say it is blood entering has a high hydrostatic pressure. Now that's due to several reasons. One of them being that it's coming straight off the aorta via the renal artery. It's very close to the heart, so it's naturally high pressure. The difference in diameter, so more blood is entering than can leave due to this increase in pressure, and also in itself having this tangle restricts blood flow, further increasing the hydrostatic pressure. It's not only saying it's got hydrostatic, the key word there is high, and then it gets higher. Ultrafiltration literally is any molecule that is small enough within the blood can pass out of the capillary, because we know capillaries from AS2 are porous, through the wall of the Bowman's capsule and into the nephron, and form what's known as glomerular filtrate. Looking at it in a little bit of detail down below here, we'll see if this is a solute molecule and it's in the blood, so this could be glucose, it could be amino acids, it could be urea. If it's small enough, it can go through the pores in between the endothelial cells. The black line, remember, is the basement membrane, and then in between these special cells called podocytes. So there's literally three layers it has to pass through. 1, endothelial cells; 2, basement membrane; 3, podocytes. The key bit is that it is the basement membrane that is the most selective. Overall, the process of ultrafiltration, as you can see, will filter molecules on the basis of their size. Now that's important to remember. So obviously there's some that can pass into the nephron, so go from the blood plasma in the glomerulus into the nephron, into the Bowman's capsule, and form what's called glomerular filtrate. There are those that cannot. So keep in your head a list of what can pass through. What characteristic must they have? They must be small molecules. Why? They need to pass through the basement membrane. Remember, the basement membrane is the most selective. So we have glucose, amino acids, ions, water, urea, and small proteins. What cannot pass through? Obviously there are large molecules, cannot pass through the basement membrane, or even probably between the endothelial cells of the capillary, blood cells, and large plasma proteins. Now the bell stopped. Now you can see what has passed through are molecules that the body would potentially like to keep some of. Doesn't want to get this back. This is an excretory product, but certainly it does not want to lose glucose and certainly amino acids and some ions. So there'll be a process after this where those things need to be reabsorbed. But we need to now look at actually the whole force, the driving force for ultrafiltration. We're going to use the example as appears on page 10 of your textbook about the driving force for ultrafiltration, and it's all water potential dependent. And we know that the water potential depends on the sum of the psi-s, solute potential, and pressure potential. Now this isn't plant cell, but there is a pressure, and that's the hydrostatic pressure we're referring to this time. So if we look at blood plasma, now it has a lot of solutes present, so it actually has quite a negative psi-s. When you compare that to in the Bowman's capsule, there are fewer proteins in it. The big plasma proteins cannot get through because they're too large, so it's less negative. In the blood plasma, there's a high hydrostatic pressure. Remember, that's created by the twisting of the Bowman's, or the glomerulus, the fact that it's coming off an artery, the fact that the afferent has a greater diameter than the efferent. So when you put those two together, we get a water potential of the plasma of 2. Looking across then at the glomerular filtrate, there's a very low hydrostatic pressure, simply because there's less fluid in it and there's no pulse wave coming with it. So the water potential of the filtrate is 0.7. Now that then gives us a net filtration force of 1.3. I know you might find it because it's probably the first time you've seen a positive or above 0, but don't worry too much about that. The point is, this is the force that wants to draw water into the glomerulus, but there's a greater pressure forcing water out. So it's the sum of these two gives us a driving force out of positive 2. This is the force that's trying to draw water in. This is putting it out. So we have a net force here. This is greater than this. So the balance is, this is trying to force water out of the renal capsule, or the Bowman's capsule. This is trying to force water in. We get a filtration force of 1.3. And it's as that water moves from the glomerulus into the Bowman's capsule in that direction that all the things that are small enough to pass through are carried. That is, the glucose, the amino acids, the ions, the urea, all pass through. If it's small enough, it passes.